So yeah, throughout the week we did a lot of pair and peer programming
On Brighton Pier.
on the Brighton
Yeah, I was
Pier.
gonna say pier as on the pier, right? Yeah.
Yes.
Is that picture
It's
is that picture literally on the pier, or is that picture at your
Yeah.
Airbnb?
We went there.
Wow,
Yeah, just for that joke. No, but
that's great.
uh, we also did some mob programming, which yeah, basically Niels, Jeremy, and I had a 3-person team, and so that was we found it a really cool format where basically we took turns every 15 minutes switching who's programming, and the other people would watch on the big screen and kind of give input, and it was a really effective way to kind of make decisions together and figure out things quickly together. And we also had a whiteboard to talk through things as they came up. Here's a short video of Monty learning on the screen, and then some people watching, contributing, watching Monty learn. Again, there's Monty moving around. Yeah. And then yeah, we also had daily check-in calls at 5 p.m. UK time, and I think 9 a.m. PT with Rami and Jose, who unfortunately couldn't join in person.
Oh, I didn't know that. Okay.
Yeah. Jose unfortunately got sick last week. And then, yeah, one of the evenings went to a real British pub, having some pints and British food. And yeah, this is the prize that you'll get to award to the best team. So we have, yeah, with the proper UK weather in the background.
Right.
It has an umbrella and a sun hat because you never know what you'll need.
Gotta be prepared.
Yeah.
Is that a Monty Python reference in the corner of the can there? Glorious Spam?
Yeah, you mean the night? I don't know.
Yeah.
I imagine they probably are kind of like unofficially alluding to it, but I don't know. Yeah.
There aren't any Vikings.
Wow.
Glorious. No, but
That's not
Monty
nice.
Python,
Wasn't-
you know, in the Holy
Didn't-
Grail,
Yeah.
like
Didn't they have a skit about Glorious Spam or something like that?
Yeah.
There aren't any Vikings in that skit. No,
yeah.
Guys in armor.
Well, you know.
Scott, did they give you any trouble in customs with you carrying those?
The only trouble I had with the extra suitcase is that I didn't really remember what it looked like.
Oh no.
As it was
And you
coming
didn't put a
down, I was
tag on
like,
it.
Yeah, I had to inspect the numbers, you know.
It's pretty generic looking as well.
Yeah, I should have put like a ribbon.
Very
on it.
generic. Basic black suitcase. There's millions of them.
The one the police were standing around waiting for someone to.
Okay, yeah, so now the idea is that each of the 4 teams has a maximum of 10 minutes to do a quick presentation of what they did this week and why it was important, and yeah, just kind of a quick presentation. It's great if you take less than 10 minutes. Try not to take more than 10 minutes. And for the judges, hold your questions until the end of the presentation, and then you get to ask all the questions you have. So good?
Sounds good.
I love those graphics.
Yeah, thank you.
Question, how did you choose the teams?
We first chose the projects, and then people signed up for the ones they were most interested in. And we just kind of made sure we got people on each of the teams.
And tried to like mix sort of departments, I guess, a bit.
Yeah.
I was interested in their project, but I'm not going to work on something that hard.
With timing and giving like a 2-minute warning at 8 minutes as well, or
Sure, yeah. I can give a 2-minute warning.
I think we're gonna be done in 4
Or-
minutes. Yeah.
Okay,
yeah.
cool.
Let's try.
Well, I'll give you
It's a lot of work. That's the show.
Okay, so we were team Python 3.8 to 3.NE thing. The reason being that we are currently pushing a big boulder of AGI up a really steep hill, and the habitat simulator is forcing us to stay on 3.8, Python 3.8, which is making everything slower and harder to get this boulder up the hill. So that was our project. We need to stop habitat simulator from slowing everyone down.
That's great.
Okay, so this is a pretty simple diagram of all of the problems and things that slow down the engineering process that Tristan put together, and Vivian and other members of the team have had input into this. But essentially, it's a reality tree. We're going to focus this project focus on that green blob at the bottom, which if we zoom in into here, looks like this. And so there's a bunch of boxes that this POC, this proof of concept, was going to try and fix and deal with. Okay, so this is the existing architecture from our proof of concepts perspective. So a benchmark, which is currently constrained to Python 3.8, contains an experiment, Monty doing all the work, and the habitat simulator, which is what's tying us to Python 3.8. So essentially a benchmark starts up and it builds an experiment, and then Monty starts requesting patches from the habitat simulator and then doing things with them and sending movements to the habitat simulator. We wanted to get to an architecture that looked like this. So we have the benchmark, which again contains the experiment on Monty, but that can now run on any version of Python. We'll have a look at what version we got to in the demo in a moment. And then we were going to have extract the habitat simulator out over the network and make network calls to it instead of it running in the same process as the benchmark. We opted to use gRPC, which is a over network protocol that Google brought out in 2016, and it's pretty good at sending large amounts of data back and forward over the wire. This architecture will also allow us to start putting in different simulators. So Isaac Gym in C++ or any simulator that comes out, we should now be able to like switch them out and use them much more simply. Okay, so what we did, and feel free to jump in. So what we did with a lot of this was Tristan and me, pair programming, and peer programming as well on the peer. So we did refactoring. So we looked at the existing classes and we found things that just we don't actually need in the protocol that we send to the simulator. So we got rid of a whole bunch of things and had to go through and look at all the code that touched these and move them around. A lot of refactoring. We did pair programming and peer programming, as alluded to earlier. And we did typing, lots of typing, and lots of typing, adding types to all of the objects within our code. So you can see on the left in the red what it used to be, and the green on the right what it is now. And so on the left, we can see it's just like NumPy array and then 0, 0, 0. And that could mean anything. But on the right, you now know it's a Euler angle, XYZ. And so those coordinate systems, if you look at this code in the future, you know exactly what it does, which is a great benefit to anyone who comes to our code in the future. It also made our code a lot smaller. So on the left, we have a function that essentially clones some data. And on the right, with the new typing, we have that exact same semantic stuff happening in half the line, less than half the lines. And so typing also allows us to write smaller and more meaningful code, which is cool.
Is that what the word blind? Is that what the word blimey means? Is it?
It's an expression of surprise that comes from an English derivation of God blind me.
Aha!
Blind me.
I was actually, wow.
I knew that question would come up, so I Wikipedia'd it.
I was impressed.
Is this, let me check. No, it's not. Okay, good derivation. So this is the code that now exists. This is the class simulator protocol. This is the Python version of how you create the simulator instance, and it has functions in it. I'm just going to put one in here, the add object function, which takes a name, the position, the rotation, the scale, semantic ID. And if there's another object in there, we're doing something important like, I don't know, compositional objects or objects including other objects. That's what the primary target object talks about. And then inside there are some functions that you can call, like take a step. So the next step in the experiment, reset the experiment, close the experiment. On the simulator side, the gRPC side, there is a receiving object, which is written in a system called protobuf, which is this thing that Google came out with, which is what they use internally to do all their network data transfer. And so you can see there's that add object, the step, reset, close, remove all objects. And then this is what a message looks like. So the thing that will get sent across the wire is essentially set up here. And then there's some more interesting data types. So when an observation is returned, it contains an agent observation, a sensor observation, and the repeated sensor observations. And that's it. That's the code. I'm not going to go too much more into code. There was thousands of lines changed over the last 4 or 5 days, but it all resulted in this exciting piece. I'll hand it over to Tristan.
And so the demo is, there's not much to see out of this, but what I want you to focus on is the idea that on the bottom here, oh wow, it looks much more lively on my screen, but yeah, actually it's probably more readable on your screen. It's moving faster than we can read on the actual monitor. So on the bottom, on the right side here, what's important is that Python 3.8. So this is the simulator running. There's actually 25 simulators running. Those are just different numbers of the simulators that are running. And they're getting messages. They're moving the simulator around and sending back what the simulator sees back to Monty. And then the exciting part is up here. That's Python 3.12, and that's where Monty is running on Python 3.12. This is where I started.
Right. So I'm sorry. This is the new stuff, right? So, but isn't 3.12 older than 3.8?
No, it's new, I think.
No, it's
Why would
it's 3.8 became obsolete last year. 3.9 becomes obsolete.
Oh, Oh, I see. This is 3.12, not 3.1.2. Got it. I'm sorry.
Yeah.
Sorry.
Much newer than 3.8.
And
Right,
so,
right.
So yeah, so that's it. It's evaluating. We're 95 episodes in. This is what a normal benchmark run looks like. One caveat to this was we can run on Python 3.12 and about 10 times slower. So that's exciting. Because everything has to go across the network. And so the serialization of data, of essentially just sending screenshots across the network between the two processes, makes it about, I would say, probably 10 times slower than if we just all run it in the same process. So
Did you anticipate that?
yeah, some level, just didn't know how much slower it's gonna be. So 10x slower is interesting. Hard to tell.
Is that still make this valuable, or it's a big hit for this separation, right?
Yeah, it makes it questionable whether we should adopt it or not. So we'll see.
The next hackathon, you can figure out how to make it faster.
Exactly.
And you can mention some of the other benefits you mentioned during the pitch of like any problems with installation are now associated with.
Let me see if I can.
Yeah, and I wonder, even just things like some of the basic transforms could maybe happen in the simulator.
So just cutting it off all the benefits that we listed for it. So kind of going into what Will highlighted, why this would be good if it worked faster. We could install Monty from the way people usually install everything in Python, pip install Monty. Right now, to install Monty, you have to use a Conda environment, which makes the setup more difficult than what Python people are used to. We can use later Python. We can use latest dependencies. A bunch of dependencies are updated in this 3.12 version. We can run on our MacBooks natively. Right now, we're acting like we are on Intel PCs. We're lying to the environment, but we could run on MacBooks natively, which is what the new version does. We can measure Monty performance separately from the simulator because now Monty is just running by itself and simulator is a completely separate process. The big one is any installation problems. So like Monty would be just install Monty and it's installed. And all the installation problems we can now blame on Habitat. Of like, hey, it's not working. It's like, oh, but that's because you're installing the Habitat simulator. So that's a Habitat problem. So that separates nicely the blame. We start getting the blame for it. And then other people can write simulators, as Will alluded to already.
Also, like installing it on Windows is currently difficult for anyone because of Habitat, but people don't realize it's because of Habitat, and then contact us.
So Habitat is a significant constraint. So this is one way of removing it for 10 times slowdown.
In the VOC. We think it'll get faster. We'll see.
Yeah, I think you can go faster.
Is that 10 times? I mean, some of those other benefits are quite significant. So is the 10 times faster? Is that overall or just this piece that you tested?
It's just a guess based on what I've seen. It's not I wouldn't quote that. It's just an order of magnitude. I wouldn't.
I mean, that would be an entire experiment, not just this section of the.
Yeah, we'd have to see how to measure all the benchmarks, etc. This is like hacking through a benchmark to kind of get things working. It's probably to get a representative number that would require more work.
I'm just curious if it's because the benefits are great, but the speed down, is pretty bad. So it's like.
Yeah.
By the way, I'm getting a sort of a weird echo when I talk. I'm not sure if someone's got their mic on or something.
Maybe Terry, if you mute yourself.
It looked like it was coming from her.
I feel like we've never had to think too much about the amount of information that's being transferred kind of for this sensory processing and things like that. So yeah, it feels like there's a lot of low-hanging fruit that could probably optimize this, like particularly the images
Right.
we are kind of sending across. And
Yeah.
the beauty of Monty is that it needs very simple input features, and so it's probably excessive what we're sending right now.
Yeah, and also with like the touch policy, we could send 4 actions at once and then just get back.
Right.
And the encouraging thing is we're now living in a time where I can play high resolution video games over a network using a cloud computer in real time. So like we know that sending data fast at human like 60 hertz plus is possible. So it's sort of like we just haven't done it here. But that can become like an entire effort. But it's not impossible to do it very fast.
Got it.
Tristan,
Excellent.
All right.
yeah, just a question. You said you're running 25 instances of the simulator.
Yep.
Could that be why it's slower, or is that not?
That's not why it's slower, because today I learned that when we run benchmarks, every episode creates its own simulator.
Oh,
When you run parallel and there's like 16 CPUs, then you have 16 simulators running.
Yeah, interesting.
Any other questions from the judges? All right, who wants to go next?
I'll go.
All right.
So Jose and I paired up on something we've been wanting to do for quite a while, which is to improve our model-free saccades. So saccades are eye motions. You dart around your eyes to look for to scan objects more quickly and identify what the object is more efficiently. So let's say in real life, as a human, you encounter some unknown entity, and you need to rapidly identify it by scanning your eyes across it, because it may be a vicious beast, and you may need to run away from it. You may need to react to it. So in reality, what you might do is what's on the left here. You might look at one eye, look at the other eye, nose, mouth. You're not aware of this, but your eyes are going to be just sort of darting around to these most salient features, most interesting and informative features. On the right here is more what Monty is currently doing with the distant agent. Yes.
Nicely.
Yes. As you can see, it just sort of starts somewhere, and then it just sort of does this sort of random walk in the fixed lengths. It may or may not find anything interesting and informative for a while. So essentially, Monty is a bit like this. And where we want Monty to be is more like this. Just making a few cool, calm, collected motions and rapidly identify what the object is.
And by the way, whose dog is that?
Mine.
I think it was yours, Jose. And then,
Arthur.
and we're just talking about the model-free eye movements, right?
Right.
Because we still have model-based eye movements. This is just the model-free ones.
That's right.
Yep.
Yeah.
Okay, so better sound detection.
Yep.
Right. It's interesting just to ask yourself the question: how do we know that dog is friendly? It's really, you can tell right away the dog is friendly. What features of the face tell that? Side point. It's just interesting. Okay.
So the idea of this week is we're going to have a Salience Showdown. We're going to try different Salience metrics, and we're going to try to possibly pit them against each other if we can, but definitely pit them against what Monty has right now. And we're going to see, who walks away from this fight, and who's the fastest draw in the West.
Is this a suggestion you're really trying to get that spam trophy? Is that the idea there? You're plugging yourself?
No.
And what was the prompt you used for that image?
No. So the very first thing we had to get going was what's called inhibition of return. So if you have a really salient location and you aren't encouraged to explore other parts of the image, then there's nothing preventing you from just staring at that one really salient, interesting part, or constantly returning to it. So what we're seeing here is on the left, we've started our gaze at the center of the cup, and that little dark spot is indicating lower likelihood of returning to it. After a couple steps, we've got a couple of these points now. So those are spots that we don't want to return to. And as you can see, over 8 steps, they sort of accumulate, and it helps us pushes us to explore other parts of the object and not.
Okay, so the red areas where you did fixate already, and the gray areas where you're fixating, and red where you were already. Is that what it is?
The gray actually indicates where you're going to go next. It's just part of the visualization.
Okay, it's next, but the other ones would be where you have been.
Correct. Yep.
No.
So this is just kind of a part of the piping we had to get going first, in order to start working with the salience maps. But even this alone, we went from taking an average of 39 steps at best with a random walk policy to identify an object, all the way down to 21 steps. So just that alone gave us like a pretty enormous performance benefit. So it's a good start.
So there's a question there about how you did that, because you're trying to find salient spots, I assume, or not yet. Maybe all you're doing right now is just inhibition return, and you didn't really try to improve. You didn't really focus on saliency.
At this point, no saliency. It's just uniform on the object. This is
got it. Okay.
Yeah.
Because there is a trade-off between like saying, "Oh, don't go back there," but also like some places you could go are not very interesting. So
yeah,
it's a balance between picking salient spots and not returning.
For
But
sure.
right at the moment, right now you're just saying random, don't return.
Exactly. Yep.
Yep.
Or at least don't return for a while, because these spots do sort of ease over time. Like you see that central spot, it's like less pronounced after 8 steps. So
Yeah.
Right.
So you can eventually return, like maybe after 10 steps, but you're not like completely like you're barred from going back.
Yeah.
Yeah, but after the inhibition of return, we did test some saliency, non-deep learning based saliency methods. So I showed here are the like 4 saliency methods that we kind of focus on. There's a lot more, but we didn't implement them all. One is called spectral residual. So this one basically does fast Fourier transform, which means we're going to filter out for low frequencies and keep like the interesting parts, which in this case are high frequency areas, usually edges. The biosaliency one on the top right is something bespoke that's Scott made. Maybe you can explain that a little bit more because we're going to focus on it. Minimum barrier is like a recent, as in 2014, computer vision method that it was kind of focused on trying to pick out foreground regions from backgrounds. So this is a little bit better for kind of segmentation, like if there's a cluttered background. This is good for kind of picking out areas in the foreground. And then the last one is idiot coke. So this is a very bio-inspired method that kind of combines like Gabor filters, has implementation related to like center surround differences. Yeah. So this is like a kind of a complicated, more complex bio-based method. Next slide, Scott. Yeah, I've also tried this out. Oh, the different, the spectral residual methods. I've tried it out on natural images as well, just out of curiosity. This is just one example, but it makes a demon dog basically. So this is Arthur, and the good boy is Arthur, when he's sleeping or kind of, low energy. The demon boy is when he's having zoomies. That's what I see when.
Which filter, which method is this?
Scott, okay, this is idiot coke. Okay.
Yeah. You can see his eyes pop out though, which is what you want. You want to be attending to that. Yeah,
but it's
teeth.
interesting. Yeah, the teeth, but also there's something above his right ear, which is not really interesting at all, and it's highlighted very much, which is
Also,
feels like a fail.
Some kind of model-free segmentation method to help constrain motions on an object.
I mean, I had to look really hard to figure out what's going on up there. It looks like it's because it's blue, maybe, and there's no other blue.
Right.
That's weird. That's weird.
This one doesn't.
Yeah. So, for example, we could apply like different saliency methods. Like if I apply the foreground background segmentation first to get like Arthur out first, and then apply, this idiot coke, then we'll focus just on the interesting parts of Arthur. So, like depending on the saliency method, what it picks us as interesting is very kind of method dependent.
Well, and also clearly, this doesn't capture the biology completely because there's a bunch of artifacts in it. It's just like why,
Yeah.
But it gets the teeth. That's pretty good.
Yeah. Kind of important if you need to run.
So the method we're gonna be working with for the remainder of the talk is this. It's essentially a combination of filters that are known to exist in early primate visual system. So we've got sort of a luminance-based filter, depth-based filter, red-green opponency, blue-yellow opponency, spectral residual. This bottom right one favors continuous-oriented regions. And so it's just a collection of 6. And we can weight them. There's gonna be a lot of tweaking and weighting and playing around with. This is sort of our.
You describe spectral residual. I'm not familiar with that.
Okay, so it's pretty similar to the one that Jose explained. With the FFT based one was looking for like higher low frequency content that's sort of above the average in the area. Yeah. So this one actually needs quite a bit of tweaking. The spectral residual, like especially the one that came out of the box, OpenCV looks a lot nicer. But there's a lot, there's still a lot to be played with here in order to get it to play a little bit better. But
yeah, for spectral residual, think about like moving across the image. Like let's say you're going through a line, it will be high frequency if it suddenly encounters an edge, right? Or like think about it that way. So spectral residual is good at kind of edge detection. I'm not sure if that helps. Anyways, go ahead.
Are we doing on time?
2-minute warning, by the way, but I think it's not your fault. I think it's maybe try and hold back your questions a little bit more, and then we can discuss it in more depth in the research meeting.
Okay.
Oh, sorry, that's me.
So we did get our improvement from 39 average steps per episode down to 23, which is great. It's actually a little bit worse than inhibition of return only, and we thought, well, maybe the reason for that is because we might actually get a bit better performance if we pre-trained our models using the same salience-driven motions than if we use the ones that were pre-trained on what's the sort of naive spiral scan, where it just takes sort of even points all across. It's sort of a very machine kind of artificial way to learn models. So we then went and we decided to learn our models. Again, this is sort of what the default is right now, the spiral scan. And this is what it looks like if you only saccade to, or you primarily saccade to the most interesting points. This here is the spam can or the potted meat can, if you prefer. And this is what it looks like if you saccade to the most salient points. And that actually did help. It drove us all the way down to 17 steps per episode. And that's fantastic. And one of the things we hope to get out of this is sparser models. And well, we'll have to get into that later, but here's a basically summary of results. This is our new state of the art. So if we just learn our models with the salience model that we've got and perform inference, we both have, so the top row is what we have currently, and the bottom row is what we have now. So we've more than halved the number of steps. That's a confusing way to put it. We're more than twice as quick at recognizing objects now. We've drastically reduced the number of timeouts, which is actually a huge time suck. It's hard to quantify it and put in the same category as steps, but it's a really significant change. And then we've also boosted our accuracy a bit. So it's super promising. I'm really excited about this. And I think that's, oh yeah, adios random walk. Yeah, so I think we have a winner. I'm very, very excited about this. It's not only did we get what we wanted, but we were able to do it in a bio-inspired way, in a principled way. And so it's a pretty exciting result for us. So thanks for listening.
Very nice.
Backup as well. Okay. Wow.
Yeah,
Yeah,
that's
that's
very
great.
exciting. You've been holding back these results.
Yeah.
It's just like every day we're checking in and talking about the results, and then today showing like,
Boom, drop, mic drop.
So I'm not taking so much time here, but it's interesting. Will and Tristan had this green theme, strange thing. You guys have introduced the red theme here going on.
now we have blue.
Yeah.
So I don't know if we've got time for questions or if we want to
Yeah.
move in.
Yeah, do you have any more questions?
Well, I was just chastised for asking too many questions. So I don't know.
Well, I guess maybe do you have questions that you'd like to have answered to make a informed decision about the winner of this?
I don't know if Terry still asked you about. I have a question. It was some of the question I asked of Will and Tristan, which is, this is one part of an overall system. This is the model-free part, and what's not clear to me how this model-free part interacts with the model-based part.
This should get us to model-based decisions much quicker. That's the idea. Like if it normally takes 20 steps before you make your first model-based motion, or motion that is derived from some kind of model-based hypothesis, this should get us there in at least half that time.
And then after we go to model-based, do we stop using the salience-based completely? Is that how it works? Or
It would continue. It would just go back and forth.
And there's a place that integrates those two in the code.
Most of the steps are model-free steps, and then every once in a while it takes a model-based step. So it keeps switching between the two. But it doesn't take a model-based step until it has some kind of hypothesis. Like at the beginning, if it doesn't have any hypothesis, it can't really make an informed model-based.
Sure, of course. Okay.
Cool.
Nice. Thank you.
Right. Yeah. Rami, do you want to go next?
Okay, so this presentation is about EMA evidence-bounded scores. Right now, what we have is evidence scores that just grow unbounded. Every time we get a little bit of evidence on any of the hypotheses that Monty has initialized, it just keeps adding them infinitely until just the evidence keeps growing. There are a lot of downsides to this. I will talk about these in a minute here. But
I don't know what does EMA stand for?
Exponential moving average. So we are averaging the evidence so that it stays bounded.
Yeah.
So I presented a little bit about this before, but right now in Monty, what we have is an experiment. An experiment is composed of multiple episodes. Every episode gets its own object, and Monty is just trying to recognize that object. After it recognizes it, we move on to another object. We reset all of the hypotheses that we had. The hypothesis could be just every hypothesis, like a guess about the orientation of the object and where the sensor is on the object right now. So we reset all of those hypotheses and we initialize new ones that match the observation that we get from the new object. This has problems when we're doing compositional modeling or compositional inference. And I think Vivian and Niels might talk about that in their presentation. But mostly what this has led to is the idea of hypothesis resampling, where every step we're always resampling more and more hypotheses, and we're also deleting the hypotheses that were not performing very well. But actually initializing hypotheses midway at any time in an episode does have problems. And one of the problems is how do we initialize it? What kind of evidence do we give it? This is one of the problems here that we're dealing with, is we could have a hypothesis that's initialized at the beginning of an episode, and it's not a very good hypothesis, but it has been there for a while. It's accumulating evidence at a lower pace than another hypothesis that is just added maybe later in the episode. And it's accumulating faster, but when it comes time to evaluate them, the one that has been added earlier actually has high evidence. this is a problem. One simple solution would be to just use the slope of the hypothesis, basically normalized by the age of the hypothesis, just divide by how many steps it has seen. But there are some concerns about, how, like, whether neurons are able to do that, whether they're able to, like, keep count of the age of the hypothesis, stuff like that. But it's one of the approaches that we're also considering. So the goal of this hackathon was to test the idea of keeping the evidence bounded in a range. So basically, we're doing this exponential moving average, where at every new step, we get the evidence that the input evidence, the step evidence, basically, multiplied by some alpha, and then add to it 1 minus alpha multiplied by the old evidence. So it's like we're always averaging, and it's always going to stay within the bounded range of the evidence. This has a lot of benefits. This basically, hopefully, it will solve this problem because the evidence is always bounded. It's just going to plateau once it reaches a certain point. And I'll show you some profiles of what it looks like on real data. This is not really real data, but simulated. Also, another honorable mention here for the idea of a membrane potential, where we're also thinking of using. So again, this is also bounded. We had to do a few tricks here to get it to be bounded, but it's basically also bounded. And the idea is that we would have to, in order to get this to work, we'd have to threshold the evidence scores so that we can convert them to spikes. And then every spike is just depositing some charge on the, just basically adding some input to the circuit or to the membrane, and then it's decaying when it doesn't get spikes. So it's another. But the problem with this is that when we threshold these evidence scores, we're losing information about how good the evidence is, or we're losing detailed information about the evidence. So we don't really want to convert to spikes just yet. So I presented this before. This was the result from hypothesis resampling. Basically, what you're looking at here, excuse me, on the y-axis, we have the evidence scores, and these are accumulated. As you can see, they can grow up to infinity. And I am switching between, so those bars at the top here, those are basically the episodes, and I'm switching between objects. And what's happening is that after we switch, we're deleting the hypotheses that are not performing based on their slopes and stuff like that, the evidence slope and things like that. But the idea is that we're deleting some of them, and new ones are being added, and they keep accumulating more evidence, and they're winning. So this is a good scenario, but it's missing some of the details. And one of the problems is if you're just looking at one of the episodes, not looking at all of them like that. So not really the scenario of object swapping that I'm displaying here, but just within one episode. We could still have that problem that I discussed before, right? An episode and hypothesis that has been accumulating evidence for a while, just not getting deleted, and a newer one that has been added halfway, just not winning the race at the time we're evaluating it here. So this here, I reran everything with EMA, and this is what it would look like with the evidence scores, with the EMA evidence scores. So the biggest difference that you would see here is that it's always bounded. So it's not going to grow above, I think, 1.5, or 2 maybe. That's the highest step evidence that we would get. So the evidence would always just stay bounded, but it will be, if the hypothesis is good, it will be above all the other ones, or the most likely hypothesis would be above the other ones, just like you see here. If the color matches, basically that means it's good. And then this is more examples of what you would see with. So this is real hypotheses, basically a few random hypotheses, just so that you could see what the profile looks like. One interesting thing here that you can see. So on the left, we have the evidence scores. This is unbounded evidence scores, and the blue lines are basically those unbounded evidence scores. And then on the right, we have the orange line and the evidence EMA, which is just on a different twin axis. When you see a line here that says 4 or 3 or something like that, that means we just basically moved from one episode to another. So this is the object swap switch, right? It has changed from one object to another. So you can see the decline in evidence EMA, and I'm basically using that decline to delete the hypothesis, right? Which I can. Sorry, go ahead.
The bottom left one, though, that one, you saw this decline before you switched to a new object?
Yeah, so there's a bit of decline. It's still in the range of 1, but the decline increased a lot when it started just not getting any evidence. But there is, I think, a few of these are actually might be a little lower in terms of slope.
I'm sorry, but would you consider that a failure in that case? Because the EMA score went down prematurely and
Yeah, it depends on how you threshold the. I should have. It's my mistake here, but I should have made these like a constant limit on the y-axis. But like this is not like this is 0.3 to 0.9. This is 0.6 to 1.2. So.
But why would it go down at all? Why would the EMA decline at all?
It's points like these where you have where the evidence it doesn't get evidence, so it would just drop because it's using the. It's dropping because of the evidence not increasing. So that's how it would decay.
So it's not just bounded; it also has a decay factor to it.
Yeah, it would decay. So here, for example, the step evidence would be 0, and if the evidence that we already have is like 1 or 1.2, then it would just decay because of that. So it's getting an evidence of 0, but it's at 1, so it would end up decaying.
And these are noisy experiments, if those are the ones you showed before, and also not always you see points that are well represented in your model. So it's not easy to get a lot of positive evidence at every step.
Yeah.
No, I just didn't understand what the actual algorithm for EMA is, and so I didn't understand if it had a natural decay.
Yeah, it might be helpful to think it's quite similar to a leaky integrated fire neuron. And so
okay, that makes a lot of sense to me.
It's
okay.
leaky in the sense that when you're not getting input, it decays
Right.
down. And what you call it. But what's interesting is, I guess, we can, by changing that alpha factor, we can essentially change the time scale for that decay and also the rise. And so one thing we've talked about, like this might even relate to kind of the multi-compartment properties of neurons, where you have dendritic spikes that last much longer versus
right.
the kind of somatic spikes, which are much. So we might end up having a mixture of these alpha constants to kind of
right.
get something similar, because we've kind of observed that it's actually beneficial to have multiple time constants.
So, but I guess I don't want to get off track here, but I was initially the current system, the blue line, this unbounded increase, that has no decay in it. Is that correct? It just has resets. Is that a correct interpretation?
It can decay. It just decays very slowly because
it's not so much decay. It can get negative evidence,
yeah.
but it doesn't decay on its own.
Yeah.
So it can get kind of inhibition, I guess.
That seemed to be the sort of decay was sort of the key, one of the key things that's missing. But and the EMA has that.
Yeah.
Yeah.
Yeah, we've been wanting to do that for a long time, and it's
And just this bounding between kind of from above to a specific value just makes a lot of things a lot simpler and a lot more interpretable. Because right now it's like, if an experiment's been going on for 400 steps, some of the evidence values are super high, versus another experiment. It just doesn't really make much sense.
Well, the bounding on its own didn't make sense to me, but if it has the bounding plus decay, it makes sense to me.
Okay.
So got it.
Yeah, 2-minute warning, by the way.
Okay, I'll be quick.
Those are important questions. I had to ask them.
Yeah. This is a visualization here that I'm going to be talking about a little bit. Mostly the parts that I want to focus on are here. You would see the ground truth object in the world, basically what the rotation is and all of that orientation and everything in the world. This one here is a correlation plot between the evidence slope and the pose error. The important part to focus on is, so every dot in here is a hypothesis, basically. This is the hypothesis space. And what we want to focus on is the pose error. So there are some hypotheses that have ground truth, good pose error, and others that have high pose error. That's just the way Monty initializes those hypotheses. And on the side here is basically the selected hypothesis. If you notice here, there's a red dot. I could click on any of those, and I would select a different hypothesis so I can inspect it and see like the evidence score since it was initialized until it was deleted, all of that stuff. So all of this information on the right is specific to a specific hypothesis, one of the dots on that previous plot. So what I noticed is when we're running these experiments, this is currently how Monty does things, it would end up choosing a hypothesis that has a high pose error, like 3.11 radians, this is like 180 degrees, as the MLH, or the most likely hypothesis, just based on its evidence, because it has accumulated a lot of evidence. Just as you can see here, this blue line has accumulated a lot of evidence because it has a high age, which means it was there for a lot of steps and it had plenty of time to accumulate evidence. Whereas we have a better hypothesis down here, which has a low pose error. And as you can see here, this looks a lot more like the ground truth. But it's only been there for 21 steps, and it has accumulated 22 evidence points. So when you compare 22 to 42, of course, the 42 one is going to win, but this one that has low pose error is the one that we want. So, sorry. So when we add EMA, that resolves this problem. You can see the EMA in the orange line, and it's bounded. It's nice. It basically ends up being a lower score for this hypothesis that has higher evidence. Even though it has higher evidence, it has lower EMA. Whereas this one has higher EMA, but it has low evidence. But this is the one we want because this is the one that has low pose error. So it ends up resolving these issues because just the EMA is a slightly better metric than just comparing the actual evidence, the accumulated evidence. I ran a few benchmarks just to make sure that everything looks good. A lot of benchmarks actually, but I'm only going to talk about one experiment. I noticed that, so this is one of the big experiments, the noisy 77 objects surface agent, and the alpha here is basically one of the EMA parameters. So I noticed that we kept the same performance. Some of the alphas increased the performance a little bit, and some decreased the performance. The problem that I've seen is with the pose error. Some of them have increased the pose error, like in most cases, pose error has increased. So and also runtime has increased quite a bit. So I think that's the part that I'm going to investigate more. There are some parameters that could tune this, like the X% threshold. Basically, how do we know when the terminal conditions has been reached? There are many details here that could be tuned that could help with decreasing the runtime, just like here, the difference between the orange and the green, without actually affecting the performance. So I think just more investigation is needed, but EMA is a plausible approach to doing this. And there are other options, but this is one of the good contestants, I believe. Yeah, so this is it.
Nice. So yeah, hopefully you guys see this.
Want me to press it?
Sure. Thanks. So yeah, Vivian, Jeremy, and we were working on compositional objects for our project. And so this is something that goes back many years, actually. Since at least we reckon 2017, people at Numenta and Thousand Brains Project have been talking about recognizing mugs, and very quickly that became recognizing a mug with a logo on it. So much so that it's become kind of something Numenta and the Thousand Brains Project are kind of famous for. So when Rami joined, or when one of our first contributors helped with the code base, the natural thing for them to do was to pose with a photo of a mug with a logo on it. So it's core to, I guess, the DNA of this kind of effort of developing intelligence. And that's no coincidence, because the whole world is compositional. This example of kind of a logo on something like a mug might seem quite simple, but it's absolutely essential to intelligence and how we understand the world, that we understand it as a hierarchy of compositional objects and how they are relative to one another. And so many of you may know that this is kind of one of the central, or really the central theme for our research right now, is getting compositional objects working. And so a lot of the cool things that people are working on, including what Rami just showed, including what Scott and Hoji showed, is about enabling us to kind of do compositional objects well. But we have been missing a way of actually evaluating and experimenting with compositional objects. Scott had made this data set a while ago that you're seeing right here with kind of objects with logos on it. But we had no framework, we had no experiments, and we had no configs, none of that to enable us to actually perform these experiments and measure that. So that was really the key aim of this project, was to implement that and get a new benchmark with compositionality. And if you don't do that, then we will continue existing as Monty currently does in kind of a non-compositional world, which is really sad, and just where everything is kind of a blurry cloud of dots associated with colors and kind of surface texture, and we don't want that. So that was really what motivated us to do this work.
Say something about this.
Oh,
This is just a bit of an insight of Monty learning about compositional objects, I guess. At first, kind of learning about the logo in isolation very frantically, and then over the first or second day, I think we got it to calm down a bit more, and yeah, just kind of move a bit more slowly over that object. Yeah, just a peek into that. But yeah, basically the kind of learning framework we set up, and we had to make quite a few tweaks to the existing framework because learning compositional objects has a few more intricacies. What we have now is split up in 2 phases. Phase 1 is learning object parts, where we basically show it the logos and the different objects in isolation. And both the lower level learning module and the higher level learning module are learning, and both of them are receiving a label at the moment. So we're kind of giving Monty a few crutches right now and not going straight to everything unsupervised. And then over time, we'll remove those. But for now, we just want to get it to learn compositional objects. So yeah, we show them in isolation and tell Monty what it is. And it learns these kind of models. And you can see the lower level model gets like a smaller, higher resolution receptive field as input. And the higher level one gets like a larger, lower resolution input. So they learn kind of different models. Like in the lower level, it's much more densely sampled. And at the high level, it learns sparser models based on the sensory input. But those are not compositional models yet. Those are just based on sensory input. And so then there's a phase 2 of learning the compositional objects, where we basically show Monty the logo, the different logo and object combinations. We have the same kind of sensory inputs, but now the difference is that the lower level learning module is actually doing inference. We're not telling it what it's seeing. It's trying to infer either like TBP logo, a Numenta logo, a disk or cup or a cube, whatever it's currently sensing. And it sends that object ID up to the higher level learning module. So then that one can actually store whatever input it gets from the lower level model into a compositional model. So here's an example that shows a model of a cup learned from input from the lower level module. And here basically the lower level module sends mug ID up to the higher one. And in this case, we still give the higher level one a label, which is the label of the compositional object. So we tell it, all right, this is a TBP mug and not just a plain mug. And then we just have a comparison condition, which we call the monolithic models, just to have like a baseline to compare to, where we don't send any input up through the hierarchy, and they just both learn these compositional models based on pure sensory input, kind of the sad world that Niels just showed.
Yeah,
So
so one of
that
the things-
actually wouldn't be compositional. It just
Yeah,
mentioned
this
that
is not
that would- it's-
composition.
Right.
So that's
It's
why we
just
call
saying,
it
oh, learn.
monolithic.
Well, yeah, but you just said the word composition. All right. So it's basically try to learn the mug with a logo is one thing. All right.
Yeah, it's learning compositional objects, but not building compositional models. It's learning monolithic models. Yeah, and that's kind of what we compare to show the benefits of learning compositional models.
Yeah, so one of the things we needed to do was to update how we measure the performance. Because initially when we ran these experiments, these are each pair of
Do you want the mouse pad?
each pair of these lines is a single experiment where we have the lower level learning module and the higher level one. And initially this would say that it was confused. Actually, no. Yeah,
Yeah.
saying it was confused. And then what we've done is we've changed it to where it says it's consistent. It's consistent with the child object of the actual object that's being viewed. So we're looking at a cube with the TPP logo, but it thinks it's a cube, and that is a subcomponent of that. And so what we had to do was come up with a mapping of, and we have much larger than this, but a mapping of, if you're looking at this, these are what the subcomponents or sub-objects, the children objects of that are. And then if the lower level module sees that, or actually if either of them see that, we say, yeah, it's a child, it's consistent with child object of it. I don't remember what these graphs are actually measuring or how they're.
Yeah,
color
yeah, it basically comparing the performance of
Yeah.
these new
And
metrics.
basically showing what we'd expect on the left, it's showing the lower level learning module accuracy of the monolithic when learning
Yeah.
compositionally,
Yeah.
and on the right it's the higher level learning module when learning monolithically or compositional.
Yeah.
And what we'd expect is, as you see on the left in the kind of light blue, the low level learning module, it doesn't know about the TBP mug with a logo, but it does know about mugs and it does know about logos. So it correctly recognizes those kind of child objects. And this basically enables us to measure this, even though there's limitations in the simulator that kind of limit our knowledge about what object is being seen at any moment.
Yeah, so then we were able to come up with some ways to collect the stats, CSV stats, and have some detailed JSON logging to kind of compare the prediction error, and then stuff with the MonDB prediction error, and kind of look at how those are measured. And then what's the next one? Oh yeah.
Yeah, prediction error space is a measure we didn't have in the code base before. So we never looked at this before. We basically added a new way of measuring
Yeah.
performance, which is like you don't need any labels. You're just looking at how well does the learning module predict its next input. And yeah, it's a nice unsupervised way to assess performance.
I think is this part of mine or yours?
That's
And then this is showing our kind of final test bed. So I kind of mentioned at the start that the ultimate aim was to have kind of a new benchmark. And so we had to change a lot of things to actually implement that, but this is kind of the final sort of artifact, which is this would basically go in our documentation. and show how performance is right now in Monty with these compositional data sets. So the aim was not to solve doing compositional models well. That's all the cool stuff that others have been working on and that we're going to be continuing on in September. The aim was actually to be able to measure that and actually run experiments that evaluates that. So that's what you're seeing here. And in particular, if you look in the top right, you see that we have these different levels. And so that's where we increase the difficulty of the compositional model or compositional object that's being presented. Going from kind of what you saw before with like a flat disk with a logo on it, so the logo isn't being distorted by the surface, up to objects with curvature, so the logo is distorted, and finally the kind of famous or infamous logo that's bent halfway through, and how you would represent that. And what these results show, which is great, is what we would expect. So firstly, if you look at kind of the correct child or parent, if you just look down that, you see in general, as the level gets increases, it gets harder, and so accuracy drops. But if you look at the top, you see the monolithic models versus our compositional models. And the compositional models get better accuracy, but more significantly, if you look at number of matching steps, they're almost 10 times more efficient at converging to the correct object. And that's because the child, or like the low-level learning module, can recognize something kind of simple like, oh, I'm seeing the disk or I'm seeing the mug, and send that information up, enable the higher-level learning module to kind of use that information. Rather than both of them just in their own kind of flat world trying to always recognize TBP mug with logo. And so,
Right, so in this case, is where they're both recognizing the same object. Is that what you're saying?
yeah, in the top two, they're both evaluated on level 1 data set, so they're looking at the same thing. So that shows, yeah, that the compositional kind of architecture is already kind of beneficial. And but what we don't have here is kind of clever policies to focus our movements on one child object, for example. And we also didn't have, for example, the resampling that Rami talked about, which is much better given that we'll often move from one object to another, and we need to kind of be flexible with our hypothesis space. So all of that is kind of benefits that we can start bringing in.
So yeah, the motto is the best baseline is the one that leaves lots of room for improvement. So yeah, we briefly today integrated Rami's hypothesis resampling, and actually got to learn some compositional objects that contain two different types of object IDs in the higher level model. So at some times it recognized the TBP logo, and at other points it recognized the disk. But there's still some bug in there. So if you actually rotate it, some of the locations are wrong. So we think there's something being messed up with the locations, and that's why it looks kind of messed up right now. But yeah, it was kind of exciting to see that the lower level model switched between logo and disk hypothesis and sent that up, and the higher level one integrated that into its model. So lots of follow-up work from this week. But yeah, we opened a draft PR there. It wasn't as simple as just creating some experiment configs. We actually had to write a lot of code and file changes, and also updated our documentation, added these new benchmarks that anyone can run. And then we also found several bugs and issues independently in Monty that we'll open independent PRs for, that were not related to this testbed itself, but just we came across as we were working with it. And yeah, the legend of logos and mugs continues. Woo!
So are you suggesting we give you extra credit for finding bugs?
No.
Couple slides to the performance measurements. Yeah, here. It also goes 20 minutes faster. Is that right?
Yeah, because it takes less steps.
45 versus 350.
That's great, because we made the whole thing go 10 times slower. You guys have made it go
faster.
So if you make all the improvements, then we can use them and it'll feel the same.
Yeah, we can just
Right.
learn everything we did this week and come out very strong on the other side.
Now, does the results change if you change the color of the logo? I mean, it's the color of the logo, the font of the logo. Does that make any difference to your results, or is it basically just focusing on text versus area?
That's a good question. Yeah, right now it would be sensitive to the color. It basically kind of picks, like, the way it's learned the logo is with a specific color. But one of the things we have in maybe we'll get to in September, is basically having a sensory processing system that understands 2D things better. And so it would pick up on things like edges, and that would be independent of color, basically. And that would be a much better model of something like a logo. But yeah,
generally with 3D objects, it doesn't rely too much on color. Color can help infer faster, but it can also recognize the same object in a different color. But yeah, since our current processing doesn't really pick up a lot of orientation any orientation features on a 2D object like the logo, like Neil said, we kind of need to add some extra processing for that.
spam.
Okay, like,
Has
yeah, the LLM that
copyright.
generated the spam can, not using the handle at all, doesn't understand 3D
But it has a copyright on it.
or composition.
Yeah, I said put a logo on it and then just put copyright.
Well, very impressive what you guys have all
Yeah.
done.